Okay, so we are going to talk about an intro to sequences. So what is a sequence? So, I mean, you actually know what this is. Like, you use it all the time. Maybe you just didn't know the word sequence. So this is just a function that computes an ordered list. So there's two types of sequences, and I'll show you examples. So a finite sequence. So this has a start and an end. So you can like count how many terms it has. So like, let's say the sequence is 1, 3, 5, 7, 9, and that's where I decide to strictly end it. So this has 1, 2, 3, 4, 5 terms. That's what makes it countable. And since it's a finite sequence, it has a start and an end. That's what we mean by finite sequence. Now, there's also what's known as an infinite sequence, and it has no end. So very similar example with a slight twist, 1, 3, 5, 7, 9, ... Now, when you see the ... that means that the pattern just continues infinitely. So you know that you're dealing with it when you see no ... That's a finite sequence versus ... infinite sequence. Okay, so let's play around with sequence notation because I think that's the easiest way to teach you it. So we're going to write the first 5 terms of each sequence. Okay, so we're just going to jump right into this. So here's my sequence. A sub n equals 1 over m. So once you know how to read this, it's like very clear what these directions are saying. So sequences are always going to start, unless you're told otherwise, you're going to really just start at n equals 1. So that's where you start. So my a sub 1 means that, so notice where I changed that. I changed it right here. So instead of now this being a sub n, this a sub 1. So I'm starting with my first term, and then where I see an n, I'm going to replace it with a 1. So this becomes 1 over 1, which we know is equal to 1. Okay, so now we continue this pattern. This was the first term. The second term is going to be denoted a sub 2. So I just increased this n by 1 here. And now where I see the n here, I'm going to replace it with 2. So this becomes 1 over 2. Got it? Okay, so what's a sub 3? That would be the next one, right? That's the third term. That's going to be, again, now where I see this n, I'm going to replace it with a 3. 1/3. And then we have a sub 4, which hopefully you're seeing the pattern now. So this is going to be 1 over 4. And then we have a sub 5, which will be 1 over 5. And so this is the 1, 2, 3, 4, 5th term in the sequence, okay? All right, so let's do this again with something that looks a little crazier. So now I've got a sub n equals n plus 1 over n plus 3. So we always start with the first term. The first term is always, let's see, I'll write it up here, a sub 1. So it's the same idea. Where I see these n's, I'm going to replace them with a 1. So this becomes 1 plus 1 over 1 plus 3. So this is 2 over 4, so that will equal 1/2. Okay. So what's going to be a sub 2? A sub 2, second term, I'm going to plug in 2 plus 1 over 2 plus 3. So what does that become? That becomes 3 over 5. What is a sub 3? I'm going to take 3 plus 1 over 3 plus 3. That comes out to 4 over 6, so that can simplify to 2/3. The fourth term, a sub 4, is 4 plus 1 over 4 plus 3, so that's 5 over 7. And the last term, a sub 5, it's going to be 5 plus 1 over 5 plus 3, so that's 6 over 8, so that's 3 over 4. Okay, so these two sequences, I kind of wanted to have everything in front of us just so we can kind of appreciate it. These two sequences, so you just see that n, you replace it, it's all good. So it's a little weird notation, I know, but hopefully that kind of makes sense. Now, this last one, I just wanted to have it all kind of in front of us. This last one I know looks a little funky. You've got this -1 to the n plus 1. So what's going on with this? Whenever you see this, this means that the terms are going to alternate in sign. So let's clear some space so that I can do this last one. Okay, so I think the key with this notation here is to not overthink it too much, and I'll show you how to do that. So let's start with the first term. So the first term we label this a sub 1, right? Okay, so if I plug this in, plug that 1 in everywhere, this is what it looks like, right? Okay, so I think it's good to like plug this in 1 or 2 times just to establish the pattern with this -1, and then you can start to trust it. Okay, so this comes out to -1 squared, and then this is 2 plus 1. So what is this going to equal? This whole thing just equals 3. So I want to write that term over here. A sub 1 equals 3, just so we can very easily visualize it. Okay, so then we move to a sub 2. So for a sub 2, this is going to be -1 to the 2 plus 1, and then 2 times 2 plus 1. So that's me just plugging everything in. So this turns into then -1 cubed, and then 4 plus 1. And that will equal -5. So I wanted to write these over here just to kind of show you how the pattern is going to establish itself. So this pattern now is always going to go positive, negative, positive, negative. So once you kind of understand, like if you don't believe this, then you can always, of course, keep plugging numbers in. But I am telling you, like the purpose of this is to alternate signs. So I already know that my a sub 3 is just going to end up being positive. So I can plug it in if I want. So let's see, this becomes 3 plus 1. So notice 3 plus 1 is 4, right? That's an even exponent, so you can tell it's going to be even. And then I can finish this. So this will end up being 7. So a sub 3 is 7. And you might even see now what the pattern with this sequence is. So anyways, why don't you pause here and try to find the last 2 terms and then hit play when you're ready. So my a sub 4 is going to be negative again. And hopefully you've noticed the pattern. So these are all odd numbers. So a sub 4 is equal to -9, and a sub 5 will equal positive 11. So that is a sequence that changes signs. Okay, so now that we kind of understand like some of the just basic ideas of computing with sequences, there are certain types of sequences I want to talk about. The first is a convergent sequence. So this is when an infinite sequence gets closer and closer to some number. So the classic example we use for this is 1 over n. So this is what we started with, right? So think about what the terms looked like. These were 1 over 1. So really, let's write that as 1. The next term was 1/2, 1/3, 1/4, 1/5. Think about this, 1/6, 1/7. So as this list continues on, what is happening here? What, like, are these numbers getting bigger or smaller? They're getting smaller and smaller, right? And there will come a point where we get to like 1 over 100 or 1 over 1 million. So once you start getting into like this threshold, especially like 1 over 1 million, you start getting to numbers that are really, really tiny, right? What if it was like 1 over 1 trillion or 1 over, I don't know, 88 trillion or whatever. So you're going to just start getting into these numbers that are super, super tiny and basically 0 at that point, right? And that's what it means to be a convergent sequence. So as the sequence continues on, this will eventually kind of go towards 0. It will never perfectly hit 0, but like the idea here is that it might as well hit 0. And if we could go on for forever, if we could take this sequence out to infinity, it would go to 0. So this is the idea of a convergent sequence, and we'd say it converges to 0. Now, there's also a divergent sequence. This is when a sequence does not converge. And these are clear. They're more obvious because they are sequences that like get bigger. So here's a sequence here. So this is the one we were just working with, right? 2n plus 1. So if I just think about like the terms of this sequence here, this will be 3, 5, 7, 9, 11, 13. This will go on, right, to like all odd numbers. So like, I don't know, 3,372,591. So like this sequence will continue with just all odd numbers, and they'll just get larger and larger. So these will just continue to increase. They don't stabilize to some number, and that's what makes them divergent. We also have things that are called recursively defined sequences. So this is when the terms in the sequence use previous terms. So let's just go ahead and find the first 4 terms in the sequence just so that you kind of get a sense of this. So the recursive sequences look a little odd. So for this sequence, notice I'm told what my first term, a sub 1 is. A sub 1 equals 3. And then look at how this is defined. A sub n equals 2 times a sub n minus 1 minus 4. Okay, so let's run this notation out. Notice I was given a1, so I don't need to compute that. Therefore, I can go ahead and start at a sub 2. So if I plug this in, this will look like this, right? There's me plugging my n in. And what is 2 minus 1? This little piece right here. This is telling us to refer back to a1. So check that out. This now needs to be used to find our a2. And that's what it means to be a recursively defined sequence. So my a sub 2 then is calculated as 2 times 3 minus 4, so that's 6 minus 4, so that equals 2. Okay, so that's the second term. Next is a sub 3. So how do we find a sub 3? I can use that same formula, 2 times a to the 3 minus, or yeah, sub 3 minus 1 minus 4. So what is this really telling us to do? This is telling us to take 2 times the previous term minus 4. That's what this is getting at. So what I'm going to do then is I'm going to take this number, right? This was my a sub 2. This was my a sub 2, and I'm going to plug it in here. So my a sub 3 then is going to equal 2 times 2 minus 4. So this equals 0. All right. So what I want you to do is I want you to calculate the 4th term and then hit play when you're ready. Remember, math is not a spectator sport. Okay, so for this last one, so now I need to refer back to the previous term. So I'm on the 4th term, so I need to refer back to the previous term. So this becomes 2 times 0 minus 4. So this is going to equal negative 4. So yes, this sequence actually is getting, like, it's going backwards. And it's totally possible that it could go backwards. There's nothing wrong with that. So this is what a recursively defined sequence is. So here's one more recursively defined sequence. So now what we're going to do with this is here's my a sub 1. So for the next terms, I take the previous term and square it. Then I add n minus 2. I think this is a really good challenge one, and I highly recommend that you pause the video, try this, and then hit play. Okay, so to get to my a sub 2, so I kind of understand this notation now. So here's what needs to happen. Oops, plus 2 minus 2. Okay, so I'm on the second term. So think about this notation. This term here is referring to the previous term. So a sub 2 equals a sub 1 squared, previous term squared, plus n. So we're on the second term. So that's why I put a 2 in there and then minus 2. So this then is 2 squared plus 2 minus 2. So this will ultimately just equal 4. So there's my a sub 2. All right, so what's my a sub 3 asking for? It's asking for me to take the previous term, which was a sub 2, and then plus 3 minus 2. So this is n. Here's my nth term. So that 3 goes there. Okay, so this becomes then 4 squared plus 3 minus 2. So let's see, that's going to be what, 17? And then for the 4th term, so this is getting very big very quickly. So would we say that this converges or diverges? This diverges. Okay, so this is going to refer to the previous term, plus 4 minus 2. So let's see, 17 squared is 289. So this will be 291. Okay, and so that is your intro to sequences. So that's just playing around with them a little bit. So I will catch you guys in the next video.